Most people know that space is mostly empty space, but what a lot of people don't know is that matter is also mostly empty space. If you shrunk the sun down to the size of this volleyball, basically this would represent more than 99.8% of the mass of all of our solar system. So all of our solar system, the mass is really concentrated in the sun. And when you shrunk the sun down to this size, the Earth would appear about the size of a grain of sand, 2 millimeters across. So you couldn't even really see it in this image. That's how small the Earth is compared to the sun. And the Earth would be about 75 feet away from the sun at this scale. That's around a quarter of a football field away from the sun. Jupiter, on the other hand, would be a little bit more than a football field. It'd be about 125 yards away. And Neptune would be almost half a mile away. And then the nearest other star would be thousands of miles away. So if you just take our solar system, it's almost all empty space. Almost all the mass is compacted into the sun. And then these distant bodies are super far away from each other, very far. And in between is mostly just space, very few hydrogen atoms. So what about matter? What if we blew up an atom to the size, what if we blew up the nucleus of an atom to the size of this volleyball? How far away are its electrons? Well, it turns out it's pretty similar to the astronomical scale. So if we blew up the nucleus of a hydrogen atom to the size of this volleyball, the electron would spend most of its time, the average amount of its time, almost half a mile away. And if we want to compare to something more like our solar system, if we took an oxygen nucleus, so let's just say that this volleyball were an oxygen nucleus, then the closest electron would be an average distance of about the same distance as Jupiter is from our sun. So if we blew up an oxygen atom so that the nucleus was the same size as our sun, then the nearest electron would be about where Jupiter is. This really amazes me. So if we take small things and blow them up to the size of our solar system, we see there's a lot of differences, of course, but there's a lot of similarities in that it's mostly empty space. Almost all of the mass of your typical atom, more than 99.9% of the mass, is concentrated in the nucleus. And yet the electrons are super far away from each other. In the same way that our planets are very, very, very far away from our own sun, and the sun has all the mass of our solar system in it, pretty much all the mass. The planets account for very, very little. Another interesting fact, a lot of people might not know this, when you look at the relative sizes of the planets, you might think, oh, well, Jupiter's only a little bit bigger than Saturn. And it looks that way, but you can actually fit all of the planets into Jupiter and have plenty of room to spare. And Jupiter represents the mass of about 2.5 times all the other planets combined. So just interesting information. The last way that our solar system, or things at our astronomical scale, look similar to things at the small scale. It turns out that gravity, what holds Earth near the sun, so Earth, if there was no gravity, no force pulling Earth to the sun, Earth would just shoot off into space. But that doesn't happen because you've got this gravity force that's pulling Earth in, and Earth has so much momentum, it's trying to shoot off, but the sun's pulling it in, so it ends up orbiting. So there's two competing forces. One is the Earth's trying to shoot out with its momentum, angular momentum, and then the gravity is keeping the planet in orbit around the sun. So that force of gravity weakens according to the distance between the two objects squared. So basically, the further you are, the force weakens by the square of that distance. And similarly, surprisingly, to me this is astounding, if you go down to the atomic scale, the same thing happens between the nucleus and an electron. The further that electron is away from the nucleus, that distance, the force is reduced by the square of that distance. So I think that's remarkable that at the very big macro scale we see a force that is basically 1 over the distance squared. So the further away you are, the weaker it gets. And on the atomic scale, the attraction force between an electron and the nucleus, or the protons in the nucleus, also weakens with the 1 over r squared, or 1 over the distance squared. One last fact I want to point out about how empty space is. So we sent off the Voyager satellites. There's 2 satellites, and we shot these satellites off, and they have gone beyond Pluto. And they've actually gone beyond something called the heliosphere. So they're well without or beyond our solar system. And what's remarkable is space is so empty, it is very likely that these 2 satellites, which are going in different directions, will continue and they will survive. They'll be relatively intact longer than the Earth will be. So the Earth is going to last billions of more years, and these Voyager spacecraft that have gone off into basically empty space, their likelihood of colliding with anything is so low, they'll probably outlast our Earth. That's how empty space is. And just know that space is even more empty when you look at matter, the stuff that matter is made of. So if you take just any piece of matter, that's mostly empty space. If you enjoyed this video, hit the like button. You can hit the subscribe button if you want to see more videos like this. And I always appreciate comments. Thanks for watching.